Hi everyone, my name is Liang and I'm the technical architecture of the DAOS and team. And today I will present, my presentation will include three parts. The first part is overview of DAOS. The second part is the ecosystem of DAOS. And the third part is performance of DAOS. First of all, what is DAOS? DAOS is the next generation object store. It is built from the ground up for persistent memory and NVMe SSD. It uses a traditional client-server model. While DAOS server is effectively called an engine, it runs fully in user space and handles I/O requests and stores metadata and data either in persistent memory or NVMe SSD. This diagram shows that DAOS can be deployed as a traditional parallel storage system. This type of deployment is really driven by density, so user can put as much as bandwidth and capacity they can get in a storage rack to provide high performance and capacity go with limited number of storage nodes. The storage node, or let's say data node, which is blue boxes in the diagram. Each node has mix of Intel Optane persistent memory and NVMe SSD. DAOS will store the persistent metadata and latency-sensitive data or small data chunk in persistent memory. Then store large chunk data chunk in NVMe SSDs. And because persistent memory can be accessed by load and store instructions directly, which means that it can significantly simplify the software design and implementation. For example, there is no need of having metadata cache because we can simply use regular data structure to manage system metadata. And then you might ask why we want to build a new parallel storage system instead of using existing one. This is because originally development of a distributed storage system was driven by checkpoint restart use cases. The application does defensive I/O in order to be able to recover from compute node failure, which means an application can dump the status of memory into storage. Then it can move forward. If failure happened, the application can read back the status and continue from the checkpoint. So the most important requirement imposed by this kind of use case is large streaming I/O, right? So POSIX file system can perfectly satisfy this kind of requirement. But today, new type of storage workloads from big data, from high performance data analytics and use case and AI are emerging. For the case of high performance data analytics, it needs native support for unstructured and semi-structured data. It means that there is a huge need of small random read and write. And so these kind of workload are not well supported by any existing distributed storage system. We also looked into those AI framework and realized that they're very different while comparing with the traditional HPC workload. Because first of all, they do a lot of reads. More particularly, different phases of AI might have different I/O workloads. Initially, it does a bunch of writes. Then it would deliver mixed write and read. And it will become more and more random read intensive for things like deep learning. At that point, output is negligible, whereas the traditional HPC workload is still dominated by write workload. So, as a summary, the goal of DAOS is really supporting different types of I/O workloads inside a single storage tier. So the storage tier should provide high bandwidth, high IOPS, and low latency random read and write. It should be able to serve these workloads at the same time. And the reason that DAOS can support all these workloads is because the nature of storage media DAOS is built on is not built on traditional, spinning disk-based storage, and the data model exposed by DAOS is also very different. We'll introduce them later. This page presents the architecture of DAOS storage on the right side and a more conventional storage system on the left side. As you can see, parallel file systems are built from the ground up with disk drive and use the kernel space block interface, which is optimized for disk drive, including using I/O scheduler to optimize disk seeking and aggregating I/O or merging them, then sending large streaming writes to the disk drive to achieve high bandwidth. At the network layer, parallel file system can do RDMA from page cache, which is good for low latency data transfer. However, because lacking unified pooling mechanism for both I/O and network event in the kernel space, so there will be plenty of thread context switch. Those kind of context switch will totally hide the advantage of low latency network. In addition, in the conventional storage system, you can still use NVMe SSD, right? You can use 3D NAND, 3D crosspoint, and SSD, and then get some better performance. But you will lose most benefits from those technologies just because of the deep software stack and user space from user space to kernel space context switch and thread context switch, and all the caches added by file system. So for those latency sensitive I/O, they can barely benefit from those new storage hardwares. On the right side, it is the new storage architecture of DAOS. It is built from the ground up with non-volatile memory. It totally bypasses all the Linux kernel I/O. So it does not do any system call during I/O on both client and server. It is an end-to-end user space storage system, and it is built over 3 building blocks developed by Intel. The first one is persistent memory and PMDK. DAOS uses it to store all internal metadata and application metadata and latency sensitive I/O, which means that all the metadata and the low latency I/O go through this I/O channel and use memory interface, load and store instructions to access persistent memory. But it will not be cost effective. It is almost impossible for user to create a large capacity storage tier with persistent memory only. That is the reason we need to have the second building block, NVMe SSDs and SPDK. We use SSDs to store large chunk data, and here we don't use traditional kernel I/O. Instead, we use the storage performance development kit and SPDK, which is also developed by Intel to provide a user space NVMe driver, so we can submit I/O directly from user space without switching to kernel space. And the third building block is on the network side. Currently, we are using libfabric interface, which is the same one used by Intel MPI. It can give us very low latency communication and very scalable collective communication over the fabric. And because our system is built for these new technologies and it is fully in user space and bypass all the Linux kernel code, so we cannot support disk-based storage. It means that if user want to use disk-based storage, then they have to use traditional storage system. And of course, when we actually start the system, there are still a few cases to do system calls to set up. For example, we need to map the persistent memory to virtual memory address space. But when the system is up and running, all the I/O handling, all the I/O submit are directly going from the user space to the storage media. This page, let's look inside the DAOS stack. And DAOS is a large capacity tier, and not like any burst buffer, DAOS manages all metadata, which means that we don't need the third-party file system in the back to maintain all the POSIX namespace and metadata. So DAOS is a standalone tier, and as presented in this diagram, in order to provide very low latency I/O, DAOS client is just a library which is integrated with the application and run in the same address space as application. And the data model exposed by DAOS library is directly integrated with all the traditional data format and middleware libraries. We will introduce this later. On the server side, you have DAOS server or DAOS engine runs on either DAOS storage node or a Linux container. It can directly access persistent memory and NVMe SSD. It stores metadata and small I/O in persistent memory and large I/O in NVMe SSD. Large I/O here is tunable, but by default is 4K or 16K or above. If the application submitted a lot of small I/Os which are stored on persistent memory, and they're logically adjacent on the offset and can make up a large contiguous data chunk or extent, then a background service of DAOS can merge and migrate them to SSD and recycle the space of persistent memory, which is very important for DAOS because DAOS is all the metadata of DAOS are stored in persistent memory. This can also resolve the defragmentation issue of the storage system and improve the performance by reducing the data index stored in persistent memory. And what is really important in this diagram is DAOS is end-to-end in user space, and the I/O goes to the library, which sends a request or RPC to the server, and the server can initiate RDMA directly from application memory into the persistent memory, or send the the data to NVMe SSD. Let's look into the detail of the DAOS cluster. An important thing we learned from software-defined storage is multi-tenancy and ease of deployment. We want to provide a high-performance storage system that can also support these features. So what we have developed is really a new data management model based on the DAOS system pool. It allows user to manage a virtual storage pool across multiple storage nodes and provide predictable capacity. In this diagram, user has a set of storage nodes. Each of them has persistent memory and NVMe SSD. The administrator can just create a pool with specifying how many storage nodes this pool should span and how much capacity on each server each server needs to have from persistent memory and SSDs. And over time, this pool can be resized, and you can provide more capacity on each server, but you can also extend the pool to span to more servers. This is very flexible, as shown in this diagram. Pool 3 actually spans across all the servers in the storage system, and it has persistent memory and NVMe SSD. And Pool 2 is only restrained to one server, and Pool 1 is created on 2 storage servers. In addition, we provide NFS with 3 types of ACL for those pools, which means that you can have different access for each pool and allocate them to different projects and different users. User can have one pool per project, so they can have predictable capacity for each project and isolate at least internal capacity. And today, we still don't have the isolation of the performance yet, but eventually we will implement this kind of QoS-like feature. This feature is practically interested to cloud service provider that wants to deploy HPC as a service. They can leverage this capability to allocate the pools to different users, so they can quickly allocate them and deallocate them and tear down the storage in a very efficient manner. Now, let's look into the details of each storage or data node. Each DAOS storage node has mixed of Intel Optane persistent memory and NVMe SSD. And as I introduced earlier, DAOS will store the persistent metadata and latency sensitive data or small data in persistent memory and large data chunk in NVMe SSD. All the user index and the space management metadata for those large I/O will still be put in persistent memory. In addition, those I/Os stored in persistent memory can be merged and aggregated, then eventually migrate to NVMe SSD. It means that SSDs are only used to store application data, so there is no metadata in SSD. All the internal metadata, like including the SSD allocated metadata, user index, user keys, are stored in persistent memory, which is very low latency and directly connected to CPU. And because all these metadata can be accessed by load and store instructions directly, which means that it will significantly simplify the metadata stack, because we can just use the common data structure, like, for example, B+ tree and a rectangle tree, and don't need to worry too much about traditional issues like alignment or disk seeking, etc. There are a few things I want to particularly explain. The first one is DAOS can benefit from many CPU cores. This is actually important because all the persistent memory access are synchronous. To provide high IOPS, multi-threads running on different CPU cores are required. And the second important thing is, if the server is a dual socket server, as shown in this diagram, we highly suggest it to run 2 independent DAOS I/O engine to minimize the cross-socket traffic through UPI and maximum the persistent memory accessing performance. Because cross-socket access of PMEM is very slow and generate a lot of performance jitter. Also, the dual socket server, it requires to have fabric adapter to connect to each of those sockets, and ideally those SSDs should also split over 2 sockets as well. This is because the DAOS design of DAOS is based on assumption that all the engines have symmetric storage capacity and symmetric I/O bandwidth. As mentioned earlier, DAOS only stores small data in PMEM, and it sends large I/O to NVMe by SPDK. In addition, DAOS has the service which is called aggregation. It can merge, extend, and migrate to SSD. And in addition, it can also merge, extend, storing SSD to larger chunks and reduce the internal metadata stored in persistent memory. For example, we have stored like two 16K chunks in SSD. We can merge them to one 32K and resend to NVMe SSD and remove those 16K chunks. Aggregation can also do something else, like for example, clean up leftover of distributed transaction of DAOS and run garbage collection for already deleted object or keys. And the last thing I want to mention is the capacity ratio between the persistent memory and the SSD should be around 6%. This estimate is based on historical data of some large data center and based on their historical data, like number of small files and the size of each files and the number of large files and size of each large files and the internal metadata size required by different files. We did a lot of computation to get this ratio, and it is possible to have a lower ratio for persistent memory, but it might require support of some future features which are still in development. Here is the details of DAOS storage abstraction. We have introduced a DAOS pool, and we also have DAOS container. It is not very well named because many people got confused by this DAOS container and Linux container. Anyway, DAOS container is an object address space for application. Each container has its own object ID space. It is also scope of transaction and a snapshot. Each object is a KV store, and an object can scatter to arbitrary number of servers within the storage pool. So you can see the container as a data set for application. It can, for example, can be either created by tool or utility or just from API. A DAOS container can be created for many different things. For example, it can be a private POSIX namespace, which has all kinds of directories and files. It can also be a block volume, can be a HDF5, which can organize its own data internally, including object, group, HDF5 dataset, and a container can also be just a KV store, which can manage millions or billions of KVs. So container is namespace, and object is the data model exported for user I/O. Each object of DAOS includes two level keys, distribution key and attribute key. So all the attribute key belong to the same distribution key will be stored on the same set of servers, and you can see the distribution key as a prefix of attribute key. All the keys are stored in persistent memory, and large values are stored in SSD, but small values could also be stored in persistent memory, as I mentioned earlier, to support ultra-low latency I/O and avoid read, modify, write for misaligned I/O. So KV of DAOS is a little bit different with other KV, because the KV of DAOS the value can either be a data blob, which is always read or write as one piece. And DAOS can also support array value, which means that user can read, write, overwrite arbitrary portion of the value. And based on this model, a lot of different things can be mapped to DAOS object. For example, POSIX directory can be mapped to KV. Each name entry is a key. inode can be value of the key, and the file can be an array object. User can submit I/O to arbitrary offsite. DAOS predefined many object classes. User or IO middlewares can choose one of those object classes to specify the data protection and distribution schema. For example, there is a three-way replication object class, and there are 4+2 or 8+2 erasure coding object class. User can use object class to define their distribution for the data distribution for aggregated performance. For example, object can scatter to one erasure coding server or 4 or 8 to get better parallel IO performance. DAOS can be deployed on a storage cluster with thousands of storage nodes and tens of thousands of storage devices. And there are two things which are important for this kind of large deployment. The first one is application can take advantage of parallel IO, so performance can scale out. To provide this kind of feature, DAOS object can do sharding IO, or let's say object can be partitioned to many storage engines. Different data can spread across different storage engines based on the hash on the key. So application can achieve very high bandwidth and very high IOPS as well as capacity, because we are providing capability of many storage nodes installed instead of one. Another factor of this kind of deployment is node or device failure is not a rare event anymore. DAOS should be able to prevent data loss by software data protection and respond to the IO request instead of blocking them when failure happens. And DAOS provides both replication and erasure coding for data protection and recovery. And both of them can protect user data by making use of data redundancy. Replication, it is very well known. Erasure coding has some similarity to RAID storage. It's also divided data into pieces to deliver both performance and fault tolerance. And the difference is erasure code consumes CPU cycles to compute parity, and it stores data pieces on different storage nodes. Or let's say replication is very simple, but it has high bandwidth and capacity overhead, whereas erasure code has complex data recovery protocol and computation overhead, but it is way more efficient on bandwidth and capacity usage. When data protection is enabled, DAOS objects are stored across multiple storage nodes for resilience. If a failure happens on the storage device or server, DAOS objects are still accessible in degraded mode. For example, application can still read data from surviving replicas or reconstruct the easy protected data in flight. In the meanwhile, DAOS self-healing system will be scheduled in the background. Similar as the degraded mode read, it can reconstruct missing data pieces from redundant data and store newly reconstructed data on a fallback node. And eventually, user data can recover to the same redundancy level, and the application can access the data in regular mode and avoid performance penalty of degraded mode. DAOS only has a flat object ID space, and DAOS does not store layout of object. Instead, DAOS uses a pseudo-random-based algorithm which takes an object ID as input parameter to compute the object layout. The locality of the object data. It means that given the same object ID and the same pool membership, storage pool membership, the algorithm can always generate the same layout. The algorithm is essentially the output is essentially a sequence of pseudo-random numbers generated by the same seed, which is the object ID. And these random numbers are indexes of storage engines, so they can represent the layout or localities of object data. And by using this kind of approach, DAOS can eliminate the needs of maintaining object layout metadata, which is expensive and difficult. And with the algorithmic object placement, all the storage engine and client can use the same algorithm as the random generator with the same OID as seed. So all of them can get the same output, which is the layout for the same object, without communicating with each other. This can significantly reduce the overall number of RPC during the distributed I/O. We have introduced the data protection of DAOS. This page includes a little bit more information about self-healing system of DAOS, which can actually recover the application data to the original redundancy level when failure happens. The self-healing system includes two components. The first component is health monitoring protocol, which is called SWIM. It is a gossip-based protocol. It can detect node failure in a certain time period. DAOS service can subscribe to SWIM protocol for failure notification and start a rebuild protocol, which is the second component of self-healing system if there is a failure event. Rebuild is the protocol for coordinating data recovery. The rebuild service, which runs a rebuild protocol, can independently discover object impacted by the failure by running the placement algorithm against its local object and determine which object have replicas or data or parity chunk on the failed server, then construct the missing piece on fallback servers in the background, even as application I/O are still in flight. In the self-healing system, the core protocol is called rebuild, and it is mainly for data recovery of storage node or device failure. However, the same protocol can be applied to another use case. This use case is called reintegration. It is really about how to bring a node back after either automated eviction or manual eviction. In this case, if an administrator brought back the failed server or engine, then all the rest engines should scan their local objects and find out if some of their objects should be moved back to the server being reintegrated. They will send IDs of those objects back to the engine being reintegrated. That engine will eventually pull those data objects back to its local storage. And the same protocol can also apply to operation, which is an operation which is called extension. So a DAOS user can add more storage nodes to the storage pool. In this case, the DAOS server can automatically rebalance data by running the scan and data migration protocol and move parts of the whole data set to those newly added storage. So user can get even more free space area and can get higher aggregate I/O performance as well. Okay, the software ecosystem. As I introduced earlier, baseline DAOS API, we are providing a new data model which exports new types of object. Our object can be can have two different value types, right? Array object which allow HPC application to represent multi-dimensional array. And we also export the native KV store object. So the new API provided by DAOS storage system is the light blue big box pattern in this diagram. We are working on different I/O middlewares and the data formats to integrate DAOS API directly with them, instead of building a POSIX system for DAOS and allow those I/O middlewares run on top of the POSIX, because POSIX has serialization constraint because streaming file is the storage model exposed by POSIX. So we don't actually build a POSIX file system. Instead, we are trying to build all those IO middlewares on top of DAOS API. Currently, we have DAOS HDFI plugin, and we have a MPIO driver. We have the direct integration of the libdfs with our POSIX, and we also working on extending the ecosystem. And the POSIX.io is supported through libdfs. I mean, the libdfs and libDAOS and the TensorFlow and the MariaDB are also in our list of IO middlewares. For example, we can just use DAOS as storage engine for NoSQL database, and because DAOS can provide almost all the advanced feature of storage engine like high performance and data consistency, scalability, and snapshot, and fault tolerance. So we also want to integrate with any existing storage tier, so user can deploy DAOS smoothly and integrate with any existing capacity tier like Lustre, S3, and HSM. We are working on data mover for them. So with data mover, we will user can migrate data set from POSIX file system to DAOS, or migrate things the other way around. DAOS provides POSIX.io support, and it is implemented as a library which is called libdfs. So it implements the POSIX files and directly on top of libDAOS. This library can be exposed to end user through several interfaces. First of all, if we have a framework like Spark or TensorFlow or MPIO or HDFI, you will be able to directly link with the libdfs with the application. So so transparently, so this can be transparent and without any change to application. And the middleware or framework will be linked with libdfs. We will have to we just have to write a small shim layer between the framework and libdfs to directly send the POSIX call to libdfs. And at that point, application is using end-to-end user space IO over the POSIX without even notice it. And but not all the application want to use the IO middlewares. I mean, use the framework like IO middlewares. Application natively built on top of POSIX, which calls the libc system call. And we first provide we provide a few diffuse daemon that provide a mount point of the DFS and can be used transparently by application. The diffuse daemon is linked with the libdfs, and which that go through the libDAOS, then access the object storage. And the DFS provide a smooth migration path, but obviously not very performant because we do a lot of communication on the client between the application and the diffuse daemon. That might be good for several use cases when performance of one single task or rank is not the most important, but still, there will be a lot of memory copy between diffuse and application. So that is why we also provide an interception library that allow us to intercept the read and write calls from the application and redirect them to libdfs. So application will do end-to-end read and write in user space without any actual memory copy. So we can provide better performance for regular POSIX.io to application without making any change to the application. The baseline DAOS API has very rich parameter and can satisfy different data models, but it is not very convenient for user, especially when most of the IO middlewares can be built on top of POSIX API, which is very different with the native DAOS API. In the meanwhile, those IO middlewares are also provide a storage abstract layer which can connect to non-POSIX storage system. This is the reason we built the DFS stream on top of the native DAOS API. And the main difference between the DFS API and the diffuse, I mean the POSIX support, is libdfs is just like libDAOS, which is a library. It doesn't have fuse and system call overhead. So using libdfs is almost as lightweight as libDAOS. User can get maximum performance from their storage system. And this table we listed most of the DFS API, which has no surprise and which is well aligned with the Fuse API or let's say traditional POSIX API. And it is easy to understand and easy to build a storage engine for all kinds of IO middlewares and benchmark tool like IOR. And of course, Diffuse is just one of the IO middlewares built on top of libdfs. We also have native Python binding, which we call PyDAOS. In PyDAOS, we integrate DAOS KV object with the Python directory, so it is very Pythonic API for users who are either not familiar with C or just want to build an application with high-level language. In PyDAOS, we can have things like iterator, bulk insertion, and retrieve operations. And we plan to support more integration with PyProp, DBM, and we also want to expose more features like snapshot and so on. So there are plenty of work to do in this area. And TensorFlow IO is a collection of file systems or file formats that are not available in the TensorFlow building support. If you check the TensorFlow IO file system operation table, these functions are quite standard IO API, which includes open, close, append, delete. So we can easily add DFS as a new file format for TensorFlow IO. And the last section of this presentation is DAOS performance. So we are actually, these performance numbers are actually from IO500 benchmark. IO500 is a community activities to track storage performance and storage technologies of supercomputers organized by the Virtual Institution for IO. And the IO500 benchmark suite consists of data and metadata workloads as well as paired namespace scanning tool. And then it can calculate a single ranking score for comparison. The workloads includes like IOR-easy, which is bandwidth for well-formed large sequential IO, and IOR-hard, bandwidth for straight IO workload with small misaligned IO transfers like 47K. And MD test easy metadata operation on 0-byte file using a separate directory for each MPI task, and MD test hard the metadata operation on small files. I mean, 3,901 byte files in the shared directory, and a finding, which is finding a relevant file through a directory traversals. So each IO500 submission should provide performance result of these workloads, and we then use them as parameter for algorithm provided by VFIO and compute out a single score for comparison of storage system. So this page actually shows the distinct DAOS IOR bandwidth. We can see that DAOS has similar performance for IOR-easy and IOR-hard. I mean, normally, those storage system, all the storage system or file system have much lower IOR-hard performance. This is which is misaligned IO, because misaligned IO could potentially trigger expensive operation like read modify write and force sharing and lock bouncings. So, but in DAOS, because DAOS has a multi-version data model, first of all the writes are non-destructive. In addition, DAOS can use different storage media in storage to store data. So we can use SSD to store the aligned part of IO and the persistent memory, which is byte addressable, to store the misaligned part of IO. So it can fully avoid the background expensive operation like read, modify, write, and has no requirement on distributed locking. And these are the reasons that DAOS can provide similar performance for misaligned write. Metadata performance is the most important part of the IO500 submission. We can see all these numbers are at the level of million IOPS. And as introduced earlier, this is really because DAOS is using PMDK and persistent memory to store both internal and application metadata. So DAOS has a very lightweight metadata stack because it can use regular data structure to manage data without using cache because it's byte addressable, and the CPU can then access those data structure by load and store instruction and avoid all the software overhead of converting non-disk format to convert the on-disk format to data structure cached in DRAM. And for example, creating file in DAOS, it really requires to insert a key, which is a file name, to a persistent tree and store the file attribute as a value of key. So it's much cheaper than and has lower latency than regular file system. Okay, the last page is really just the community resource of DAOS. So DAOS is an open source project, and all the source code is on GitHub, and we have online document and have a mailing list on Slack channel, and we also have a YouTube channel. And we had we had a few DAOS user group, and which is always I think it's November, the same time as SC, and yeah. So that's all the content I want to introduce today. And is there any question?
First of all, thank you so much, Liang, for the presentation and for the webinar. It was really insightful, and I think there's so much in there to just digest for everyone. I know for sure for me, because I work with some AI workloads in HPC space, there's tons to do there. So thank you. We have a couple of questions in the chat. I'll say that if you have any questions to the attendees, please either raise your hand and I can unmute you, or you can put your question in the chat. So let's go through the questions. So first question is, we encountered a problem that DAOS server NDDMG command did not recognize the NVMe device. Is that familiar? And is there a command that scans and checks the server configuration file?
I think we have a tool to actually automatically generate a config file for your storage server. So you can try the tool, and if there is any other issue, I think you need to provide details in this, either in the Slack channel or mailing list. So
yeah, so Dina, could you do that?
Yeah.
Yeah. And I think we can help you out that way. Second question is RDMA to memory space on one node accessible from remote node? If so, does it bypass local memory and directly go to the NIC?
Sorry, I'm not clear about the question. Could you repeat?
I think he's asking about so he's asking basically RDMA, about RDMA, and whether one node can access the remote node. And
yes.
If it does that, then does it bypass the local memory and directly go to the NIC?
Yeah, so there's RDMA is always like the path of RDMA is the client registers its data buffer as MR, then send the MR to the server, and the server can allocate the RDMA buffer, or take one of the pre-registered RDMA buffer, then do the RDMA. So if the data is supposed to store in persistent memory, then the server side RDMA buffer can be persistent memory. But if the data is going to be stored in SSD on the server side, then the RDMA buffer is actually the DMA buffer for SPDK. So we have a lot of pre-registered DMA buffer, and which can be used for RDMA. So in that case, the RDMA can go through the can initialized by the server, and so we can either we can basically get data from the client MR to the DMA buffer, then send the DMA buffer to SPDK to store the data. That's the path of RDMA. I'm not sure if it answered your question.
Okay. Yeah, and there are a couple of follow-up questions to the RDMA. So one question is, what is the DAOS RDMA protocol, and could it be easily ported over to Tofu, which is the network in the Fugaku's machine?
Yeah, I think the RDMA protocol is really just as I described. It's really the, I mean, if you're familiar with the Lustre or Elnet or Polos, it's really just a kind of RDMA handshake, right? Because so it's like client has to. We cannot do any kind of data RDMA pre-registration on the client because application buffer, or there is no, we cannot predict which buffer is going to be used by the application. So the application has to do its own part, from the DAOS client, and so the RDMA key or MR key is going to be embedded in the RPC. So DAOS IO is really a full RPC. It's like the client provide the key and the buffer and the value buffer, which is a key for the MR to put those information on RPC and send it to the server, and the server can parse the RPC and see the IO request, the content of the IO request. And this is the I think this is a very traditional protocol for distributed file system.
Right, and there's a question follow-up after that about what fabrics does DAOS support, and if Mellanox is supported.
Yeah,
and can a GPU access DAOS directly?
Mellanox is definitely the one we can support, because all the current benchmark we are using is based on Mellanox, and we also the Aurora is going. I mean, Aurora system is going to use Slingshot, and
right.
We can also support Ethernet. But as you know, Ethernet requires a lot of memory copy, so it might not perform very well for the high performance computing. So yeah. So it really depends on the libfabric. All the providers supported by libfabric, we can just use it.
Right. There's a question about usage. So does DAOS allow limiting storage per user per job?
So DAOS user can create, administrator can create and assign DAOS pool to different user or project. So the quota part is really at the storage pool level. Storage pool is, as I introduced in the presentation, is a virtualized storage pool which can span across multiple storage nodes, right? So it can be 1 or 3 or 10 or let's say all of the storage nodes in the storage cluster. So the control is really at the storage pool level, and in each DAOS storage pool, a user can create a container which is a different data set, right, for its application.
Mm-hmm. Yeah, thanks. We have just a couple of more questions. So one is, are the data movers batch, or is the plan to do sort of auto movement? So DAOS is a part of a hierarchy.
I'm afraid data mover has to be interfered by administrator. It's not an automated thing, because data mover is really it requires to serialize the container of a DAOS container or DAOS pool, and then send to the second storage tier. So when the data mover is working, it has to make sure that there is no flight IO and the pool container is closed. So I don't think we have in the short term, we don't have a plan to support automated data movement. It really has to be done by an administrator.
And so far, this is the last question we have in our chat. So this is, you mentioned that 6% for PMEM for metadata is recommended. What happens if you run out of the metadata buffer? How is the client side notified of that?
Yeah, that's a good question. So first of all, DAOS has introduced, DAOS has an aggregation as a background service, which will try to do something like free the persistent memory space. But if there is nothing it can do, then today our solution is really ask user to freeze a pool or container. So first of all, the user can migrate it to the capacity tier, right, by data mover. then it can delete the pool in DAOS tier, and when user need to access the pool again, we can bring it back. And that's one way. And also in the future, we might support we might support operations like freeze a particular container by doing so. What we call freeze is really just to serialize all the metadata in persistent memory and store them in SSD. So by doing this, we only free the space in persistent memory, and for a container which is not accessed by application, and free all the PMEM space occupied by this container. So all the container can have more persistent memory space. But it also means that the container cannot be accessed, and the next time, if user want to access the container or the pool which is frozen, an administrator has to manually bring it back. In the future, we might do things. We might have a smarter solution, but in the near term, that's the only solution we can provide.
Oh, that's good. Okay. I guess we can take one last one. Is there a difference regarding performance between a local DAOS system that is server and client on the same node and a distributed DAOS system?
We don't actually recommend that. It's because so DAOS, as I said, DAOS is based on assumption that all the storage engine has symmetric hardware. I mean, the same capacity and same bandwidth and the same CPU power. So if you put the application and the DAOS client and DAOS server on the same node, it means that the application might impact the DAOS server, right? I mean, the thread can even you're using CPU binding, but it also means that it will generate all kinds of performance jitter. So if we have performance jitter, then it will impact the data. Well, it will impact the performance DAOS data engine. So we don't actually recommend that. But if you're running DAOS server in a container and then assign some CPUs to the application, that might work. But today our typical deployment is really have dedicated DAOS server and a dedicated compute node.
Okay, thank you, Liang, for the presentation. We're on top of the hour. I see there are more questions coming in. I think if you have any questions, if you don't mind, Liang, I will direct them to you. Maybe they can get in touch with you. And thank you everyone for attending and for the lively Q&A. The recording and the slides will be made available on the IXPUG website, as well as you'll receive it in the email. Thank you everyone, and thank you, Liang, for the presentation and for the webinar.
Thanks.